Chapter or Module 12, Environmental Control and Pressurization. Environmental control and pressurization systems (ECS) maintain a safe, comfortable, and habitable cabin environment by controlling air pressure, temperature, humidity, and air quality. Because we as humans, we cannot handle low pressure environments at 35,000 feet above the earth. Okay, that's why we would need this controlled environment where it would be livable. Okay, so pressurization systems are necessary and essential for high altitude flight, allowing aircraft to operate efficiently while protecting passengers and crew from hypoxia, which is the lack of oxygen, and decompression hazards, in which a low pressure would cause a high pressure of your own body. Okay, the blood within your own body would try to escape. It would start pushing outwardly against your skin. Why? Due to the low pressure. Cabin pressurization principles. The need for pressurization: atmospheric pressure decreases exponentially with altitude, reducing the partial pressure of oxygen, okay, which can lead to suffocation. More than suffocation, you have the problem of decompression, okay? So, above approximately 10,000 feet, supplemental oxygen or pressurization becomes necessary. Standard atmosphere pressure variation, okay, pH is equal to P0, which is the sea level pressure. Okay, pH is the pressure at an altitude h, is equal to P0 multiplied by the exponential of minus m, which is the molar mass of air, multiplied by g, gravitational force, or acceleration rather, times h, the altitude, divided by RT, R being the universal gas constant, and T is the absolute temperature. So this is how fast the pressure decays with altitude, which is why it is necessary to provide pressurization, having enough oxygen in a contained environment. Cabin differential pressure. Cabin pressurization maintains a cabin altitude significantly lower than aircraft altitude. Okay, in other words, the apparent pressure within the cabin would be much higher than that at the outside of the aircraft itself. Okay, so the key parameter is differential pressure, which is delta P equal the pressure of the cabin on the inside where the passengers are sitting, minus the ambient pressure, which is the pressure of the atmosphere outside of the aircraft. Typical transport aircraft limits are a maximum delta P of 7 to 9 psi, Pascal per inch. This is the acceptable difference or differential pressure. Cabin altitude would be 6,000 to 8,000 feet at cruise. Now, we have structural considerations to be taken, to be minded. The fuselage must withstand cyclical pressurization loads. Why? Because you have the internal pressure is going, like it is pushing against the skin of the airplane, and it has the tendency to move the air to the outside in order to attain equilibrium. So you have the hoop stress against the fuselage in a cylindrical fuselage is given by sigma h is equal to delta P times R divided by T, where delta P is the difference of pressure between the cabin and the external, multiplied by R, which is the radius of the fuselage, divided by T, or the skin thickness. So let me draw it for you. Let's say this is the fuselage, a section cut of the aircraft, and these are the different passengers sitting. Okay, the radius would be from the center to the external circumference. This is R. The thickness is the thickness of the skin of the aircraft. Okay, thickness of the metal, that is T. So sigma h, which is the structural hoop stress, is given by pressure differential, or the difference of pressure between cabin and ambient, delta P, multiplied by the radius of the fuselage, divided by T, which is the thickness of the skin of the aircraft. Air conditioning systems. Functions of aircraft air conditioning. are the following: temperature control to provide a more moderate temperature that is comfortable to the passengers, ventilation and air renewal, humidity regulation so that the humidity within the cabin would be acceptable, also pressurization, air supply. Now, ACM or air cycle machine systems, most modern aircraft use air cycle refrigeration rather than vapor compression systems. So the air is compressed by the ACM compressor. Secondary heat exchanger removes the heat from the air. Then expansion through turbine produces cooling. Okay, the ideal gas relation, and you might be familiar with that from the class of physics. You have PV equal nRT, okay? Pressure times volume equal nRT. R is the constant of the gas times temperature. Temperature change during isentropic expansion is T2 equal T1 multiplied by P2 divided by P1 to the power of gamma minus 1 divided by gamma. Gamma, I'm trying to remember if it's something like it is a constant that has to do with the gas. I will pick it up. One moment, okay? And temperature control, mixing hot and cold air achieves desired cabin temperature. So T mix is equal to M1 T1 plus M2 T2 divided by M1 plus M2. This is the minimum temperature, okay, given by mass 1 times T1, the original temperature, okay, plus M2, T2, like the cooling air, okay, divided by M1 plus M2. This is the exchange temperature formula, okay, between the gas that's going in and that is existing in the cabin, okay, during a heat transfer, okay, or a cooling transfer here in this case. Another side note here is that when we talk about isentropic expansion, what happens in such case is that the gas would be expanding in volume or increasing in volume without an alteration of temperature, meaning without losing its heat or cold characteristics to the transfer system, to the pipe system. So, which is another word called a fixed entropy. So it won't lose its entropy. Plus, more than that, the process is reversible, meaning that you can reverse the process without incurring any friction or drag that will change the characteristics of the gas. Also, as for gamma in this formula, it is the calorific capacity or the heat capacity for a specific gas in respect of the volume. Bleed air systems. Bleed air sources. Okay, what is the bleed air? The bleed air is extracted from engine compressor stages, low or high pressure, auxiliary power unit or APU. This is the main starter at times of the engines, okay? In case something wrong happens, the APU would restart the engine in mid-flight. Ground air supply. Okay, bleed air pressure typically ranges from 30 to 50 psi with temperatures exceeding 200 degrees Celsius. Bleed air control, pressure regulating, and shut off valves maintain safe operating limits. Okay, the pressure of bleeding should be less than or equal to the maximum acceptable pressure. Heat exchangers reduce bleed air temperature, okay, which is Q equal MC delta T. Okay, the mass of the air times C, the calorific capacity, multiplied by the temperature at the input minus temperature at the output. Okay, so this kind of exchange for the heat and cold, it controls like the environment or the atmosphere within the cabin, and by keeping it within the acceptable limits so as to not have like an over a high temperature or a very cold temperature. Bleed air distribution. Bleed air supplies air conditioning packs, pressurization system, which is the system that keeps a pressure similar to sea level altitude pressure within the cabin, okay, to maintain the comfort of the passengers, and wing and engine anti-ice systems, which is the de-icing boots that are inflated, deflated continuously during icing conditions in order to prevent the formation of ice on the leading edge of the wing. Okay, bleedless aircraft concepts. Modern aircraft, which is like Boeing 787 Dreamliner, use electrically driven compressors, reducing fuel burn and maintenance, which is very important. Okay, so it uses electrically driven compressors to lower the fuel consumption rate. Okay, this would reduce the fuel burn and it would be better for maintenance. It would also reduce maintenance. This, in fact, would lower the strain or like the pressure on the engines. This is how it lowers the consumption of the fuel. Okay, why? Because it would be mainly driven by power, electrical power, then rather than mechanical power derived from the engines themselves. Pressurization instruments and warnings, cabin pressure indication. Okay, the key cockpit indications include cabin altitude, cabin rate of climb and descent, and differential pressure. Okay, so the cabin rate of climb is given by DHC, difference of altitudes, divided by dt, or the derivative of altitude in respect of time. Okay, cabin altitude. Pressure sensors and controllers. Electronic cabin pressure controllers, or CPC, regulate outflow valves based on flight phase. Okay, so delta P commanded or differential of pressure is given by F. It is a function, in other words, of the altitude and cabin altitude, W, and phase during the flight. Now, outflow and safety valves. Outflow valve, primary pressure regulation to like adjust the pressure by releasing some of the held pressure within the cabin. Safety valve, overpressure protection. So in case you have an overpressure, it releases the pressure to also reduce the strain and the stress against the skin of the aircraft, the fuselage. Negative pressure relief valve also to this would be to increase the pressure instead. All of these working together would keep the pressure of the cabin at an acceptable value. Overpressure condition is given by delta P greater than delta P max. In other words, for the overpressure condition to be met, the difference between the cabin pressure and the external pressure should exceed a certain threshold for it to be considered as an overpressure, which would be dangerous against the skin of the airplane and also against the passengers, okay, at times. Warnings and emergency systems. Okay, you have cabin altitude warning horn, typically at 10,000 feet. Automatic passenger oxygen deployment, which occurs when you have a sudden depressurization of the cabin or decompression, or in other words, loss of cabin pressure. And third, master caution and ECS alerts. ECS, of course, stands for Environment Control System. Time of useful consciousness decreases with altitude. Why? Given the fact that as the altitude increases, the pressure of the air, or the density rather, decreases, which also leads to a starvation in oxygen. So the hypoxia becomes more severe and more prominent. Actually, it would occur at a shorter period at high altitudes. So this is why the time of useful consciousness decreases as altitude increases. Decompression scenarios. You have a slow decompression. This is usually when you have a small leak or crack within the airframe. So it would start manifesting as a small depressurization, very gradual, very slow, and very minimum, okay, of the cabin. so it would be like a small leakage. Rapid decompression, when you have a sudden like blow in, for example, let's say you have the hole of a bullet, okay, a hole caused by the bullet that would cause a rapid decompression and a rapid loss of cabin pressure. And third, explosive decompression. This type of decompression would rip the airframe apart, okay? Like in one of the instances, it was a flight over the ocean. Don't remember the number of the flight, but what happened is that the decompression actually ripped off the entire upper part of the fuselage, okay? So, and by the way, in some instances, it brought airplanes down. So it can be very serious. Now, the cabin pressure decay is given by dP over dt, so which is the decay of pressure or the decrease of pressure in terms of time. That would be less than 0, okay, for abnormal condition. Now, summary: environmental control and pressurization systems integrate pneumatic, which is the wheels, okay, the brakes, thermal and control subsystems to ensure aircraft safety, comfort, and structural integrity throughout all phases of flight.